Hello and welcome to the second lecture of this computer vision course. If we want to build computer vision systems, we first have to gain a good understanding of the image formation process, of how a 3D scene is projected onto a 2D image. And once we have an understanding of this process, we can start developing models that mathematically formalize this process. And that is what this lecture is about. This lecture is structured into 4 subunits. In the first one, we will introduce basic primitives and transformations in conventional, but also in particular in so-called homogeneous coordinates, which play a fundamental role for describing objects and projections in 3D computer vision. In the second unit, we're going to discuss the image formation process from a geometric perspective, how geometric features are projected geometrically onto the 2D image plane. In the third unit, we'll then move on to the photometric image formation process, how light actually changes while traveling from the light source to the camera. And then finally, we're going to also have a look at how the image is then processed inside the camera and stored in the camera. Let's start with primitives and transformations. Geometric primitives are the basic building block used to describe 3D shapes. In this unit, we will particularly focus on points, lines, and planes, which are the most fundamental geometric building blocks. Furthermore, we will discuss the most basic transformations both in 2D and in 3D space. This unit particularly covers the topics discussed in the book by Rick Selitsky, chapter 2.1, and a more exhaustive introduction into multiple view geometry and their fundamentals can be found in the Hartley and Sisserman book. Let's start with 2D points. 2D points can be written in conventional or so-called inhomogeneous coordinates as a 2-vector where we have 2 real scalar numbers, real valued scalar numbers that describe the 2 coordinates. For instance, the 2 coordinates in the image domain. Now what we're going to introduce now is an equivalent representation in so-called homogeneous coordinates. That's why we call these here inhomogeneous to contrast to homogeneous coordinates. In homogeneous coordinates, we're extending the dimensionality of the vector space by 1. For 2D points, that means we have a 3-dimensional space, but actually this space has a certain meaning. This 3-dimensional space is not just a 3-dimensional space because we're removing the element at 0 and call this space P2, the so-called projective space. And this is a very important space that we're going to work a lot with during this unit and lecture. As you can see, we have augmented this 2-dimensional vector with a 3rd coordinate that is called W. And we have also introduced the tilde symbol, the tilde above the symbol, to explicitly denote that this particular coordinate is to be interpreted as a homogeneous coordinate and to distinguish this from a conventional inhomogeneous coordinate. So whenever you're going to see a symbol that carries a tilde on top, you know that this is an homogeneous coordinate that's interpreted as an homogeneous coordinate from this projective space that is simply R3. In the 2-dimensional case, it's R3 except for the element at 0. homogeneous vectors differ only by scale. Homogeneous vectors that differ only by scale are considered equivalent. That's why it's effectively a two-dimensional space, this projective space, because we define an equivalence class by all vectors that are related through a scalar operation. So assume there's a vector 1, 1, 1, then the vector 2, 2, 2 is considered equivalent. It falls into the same equivalence class. That means homogeneous vectors are defined only up to scale. Why do we introduce such a strange construction? Well, we're going to see very soon that this is very beneficial. It allows us to express points at infinity. It allows us to express intersections of parallel lines. It allows us to express transformations very easily as concatenations of multiple transformations. And in particular, it also allows us to denote or to mathematically formalize projective projections that are fundamental for 3D computer vision as linear operations. But for now, the most important thing that you have to remember is that homogeneous coordinates are denoted by a tilde, and they are representing equivalence class with a vectors in a vector space, or using a vector space that's one dimensionality larger than the original inhomogeneous coordinates. So in 2D, that is a three-dimensional space. For 3D inhomogeneous coordinates, that would be a four-dimensional space. And then all of the vectors that are related just by a different scaling are considered to be equivalent. Now, how can we convert between an inhomogeneous vector and a homogeneous vector? An inhomogeneous vector is converted to a homogeneous vector by simply adding a 1. This is a convention. If there's a 1 as the last element, then the first two coordinates are considered the inhomogeneous vector of a homogeneous vector. And so here we have an inhomogeneous vector x, and we concatenate a 1 to this two-dimensional vector to obtain a three-dimensional vector. And then this is going to be a homogeneous vector where the first two coordinates are the inhomogeneous part. And for all vectors that have a 1 at the end, we call these vectors also the augmented vector, x bar. So we introduce another symbol that we can put on top of these vectors, which is a bar. And this bar denotes that we have a homogeneous vector. It's also a three-dimensional vector, but it's one particular element of this equivalence class, which is exactly that element that has a 1 as the last entry. And there's only one such element. So it's one particular element of all possible homogeneous vectors that are equivalent to each other. And this is how we define the relationship between the inhomogeneous vector and the homogeneous vector. Now this also allows us then to, of course, convert in the opposite direction. As you might have already realized, to convert in the opposite direction, we simply have to divide by the last element of the homogeneous vector, w tilde. Because if we do so, the last element of the vector turns into a 1. And so we can read off the inhomogeneous vector from the first elements of the vector. So here's an example. We have an homogeneous vector x tilde with the last element a w tilde, and we divide this by 1 over tilde. So we get x tilde over w tilde and y tilde over w tilde and w tilde over w tilde, which is 1 as the last element. And so this is then, as we see, an augmented vector, because by definition, the last element must be 1. So the inhomogeneous vector is x tilde divided by w tilde and y tilde divided by w tilde. So we gained, we see the relationship between the homogeneous, the inhomogeneous, and the augmented vector here all in one equation. there's one special homogeneous vector that has a special meaning, and that's the homogeneous vector where the last element W tilde is equal to 0. And such points are called ideal points or points at infinity. And these points can of course not be represented with inhomogeneous coordinates, because if we have W tilde equal to 0, we would have to divide by 0 here these two elements, which would lead to infinity for the x and the y component of the inhomogeneous parts. However, this allows us to very conveniently express points that are located at infinity, even without having to use the infinity symbol. We can simply have a vector, a homogeneous vector, where the last element is 0. And the point that corresponds to that homogeneous vector is a point that lies at infinity. Here's a visual illustration of this, of the relationship between homogeneous and inhomogeneous and augmented vectors. We have the homogeneous coordinate system here, x, y, and this should actually be a w. And then we have the homogeneous vector that's represented in that coordinate system. And we have this plane here that is a plane in the xy plane of the homogeneous coordinate system, but translated to the location where z or w actually is equal to 1. And so if we divide this vector here by w tilde, we obtain this point here that is on that plane, where the line that connects this 3D point and the homogeneous coordinate system intersects that plane that defines the inhomogeneous coordinates. And at that point, we have the augmented vector with the last element being 1. And you can already see that this model or this projection that we are doing here by division resembles a lot the perspective projection process that we're going to discuss later. So it's kind of intuitive that this is a useful thing to do, a useful representation to have. But we'll see precisely what we can do with this homogeneous representation in the next couple of slides. Now, given this homogeneous representation of points, we can also express lines using 2D lines using homogeneous coordinates. If we want to express a 2D line using homogeneous coordinates, we also write L tilde. We're always using bold symbols, by the way, to denote vectors, bold lowercase symbols. We use bold uppercase symbols to denote matrices, and we use non-bold symbols to denote scalars. So we have a line that is a free vector ABC, and if we multiply that free vector ABC as an inner product with a augmented vector x bar, we obtain this expression here, ax plus by plus c1 equals 0, which we recognize as the line equation. For all points that are located on the line, all points x, y, if this equation here is 0, these points are located on the line. This is the definition of a line. All points that satisfy this constraint are on the line. And so we can write this in this explicit as this explicit expression here, but we can also simply write this in terms of a inner product between the homogeneous line vector and the homogeneous point, which in this case is a augmented vector. But of course, note that it doesn't need to be an augmented vector. The augmented vector is just one element out of this equivalence class of homogeneous coordinates. So we can scale, we can use this line equation holds for any other homogeneous vector, because we know that all of these homogeneous vectors that are related by just scaling are the same. So we can divide or multiply this equation here on the left-hand side and on the right-hand side arbitrarily, and obtain still a line equation. We have just chosen here, for convenience, the augmented vector x bar, because this gives rise to exactly this line equation that we're familiar with. But of course, multiplying both sides doesn't change anything. Now, for instance, what we can do is we can normalize L bar, which is also a multiplication with a scalar, such that L bar, the line, becomes nx, ny, and d, or nd, which then has a particular geometric meaning, where this n, we normalize it in a way such that this n vector is normalized to 1. And in this case, n is just a normal vector perpendicular to the line, and d is the distance to the origin of the coordinate system. Okay, and I have an illustration for this on the next slide. An exception, or a special line, is the line at infinity, which we denote as L tilde infinity, which is the line defined by the vector 0, 0, 1. And this is the line that passes through all the ideal points, through all the points at infinity. Now, of course, we can't normalize this line such that it is in that representation, because we would have to divide by 0. And that makes sense, because that line is at infinity. We can't represent it in that normalized way. Now, to describe some of the properties of what we can do with lines, what we introduce is first, or what we remind ourselves is first, the traditional cross product that we know from school between two vectors. The cross product is written as, if we have one vector A and one vector B, AXB. And we can also express this cross product as a skew-symmetric matrix and a vector. Here we can see how this is looking, or how this is written mathematically, with these two brackets and the X symbol. And this skew-symmetric matrix is defined like this, such that if we multiply this with the B vector, we get the familiar form of a cross product between the vectors A and B, where the elements are A1, A2, A3, and B1, B2, B3. Another remark here, in this course, we are using squared brackets to distinguish matrices from vectors. So whenever we have a vector, I'm trying to write a non-squared matrix, a non-squared bracket. And whenever we have a matrix, I'm trying to write a squared bracket to distinguish the two. You can see we have one matrix here, and a vector here, and another vector here. Good. Now, in homogeneous coordinates, the intersection of two lines is given by a very simple form, or as a very simple expression, using this cross product definition here. What we have is that this point x tilde, everything in homogeneous coordinates, is equal to the first line cross product the second line vector. And similarly, the line joining two points can be compactly written in homogeneous coordinates as L tilde being equal to the first homogeneous point cross product the second homogeneous point. And here I've used the augmented version of an homogeneous vector, but this could be replaced by any homogeneous vector, of course, again. The symbol here denotes the cross product, and the proof of this is very easy and is left for the exercise. So we see already that this homogeneous representation is a very useful representation to express very simple relationships that are otherwise harder to express. Here's an example. So here we have two lines. One line that is characterized by the equation y equals 1, and another line that's characterized by the equation x equal 2. The line vector for the first line is simply 0, 1, minus 1, because if we multiply this with the augmented vector x, y, and 1, we obtain y minus 1 equals 0, or y equals 1. And similar, the line vector for the second line is 1, 0, and minus 2, because we want to express x equals to 2. Now, if we take these two line vectors and compute the cross product, which can be also written as this product of this skew-symmetric matrix with the second line vector, where this skew-symmetric matrix is simply specified as this cross product matrix, which I have again written here on the slide on the right, and we multiply these two together, then we obtain 2, 1, and 1, where we see this is all directly, it's not a arbitrary homogeneous vector, but in this particular case, it's already a augmented vector with the last element being 1. So we can directly read off the inhomogeneous coordinates 2 and 1, and we can verify that 2 and 1 is indeed the correct intersection of these two lines. We can also do the same for two parallel lines. Here we have two parallel lines, 1, 0, and minus 1, and 1, 0, minus 2. And if we do the same thing now for these two parallel lines, we obtain as the intersection point 0, minus 1, and 0. And this intersection point, as we can see from this homogeneous representation, is at infinity as expected. Right? So these two lines are indeed intersecting at infinity because the last element is 0. It is an ideal point. The outcome of this operation is an ideal point. And we can also take the line at infinity and multiply this with the point at infinity and verify that indeed the inner product between these two is 0. So the point, in other words, the point at infinity does actually lie on the line at infinity. Okay, so we've seen that homogeneous coordinates allow us to express points at infinity and very easily the relationship between lines and points. We can also represent more complex algebraic objects using homogeneous equations. For instance, if we go from linear equations that we had discussed so far to polynomial equations like quadratic equations here, in this case, we can express conic sections. So here we have a quadratic expression, and the solution to this quadratic expression is a conic section, which is a section of a cone with a plane. And this gives a result to such a curve here. And depending on how we orient that plane, which is defined by the Q matrix, we get either a simple circle, an ellipse in this 2D space, a parabola in this blue 2D space, or a hyperbola in this 2D space. And this is very useful for multi-view geometry and camera calibration, but we're not going to discuss this in very great detail here in this lecture. And there's an entire book written around this, which is the Hartley and Sisselman book, which I recommend to have a look in case you're interested in more details about this type of representations and how they relate to camera calibration. Now, let's move on from 2D points to 3D points. Similarly to 2D points, 3D points can also be written in homogeneous coordinates. Here's an inhomogeneous representation of a 3D point, and here's the corresponding homogeneous representation of a 3D point, where we now have a projective space P3, which is the four-dimensional vector space except the element at 0. Right. So this element we remove because we have to define the direction of the vector. So W tilde can be 0, but not all of the elements of that vector can be 0. And that's what's called the projective space. The origin is removed. Now, similar to before, well, first of all, similar to before, all homogeneous vectors that are related by scale are in the same equivalence class, and we can convert between homogeneous and inhomogeneous vectors in the same way as before. For instance, we can go from a homogeneous vector to an inhomogeneous one by dividing by W tilde. We can also represent 3D planes as homogeneous coordinates, where now the plane is represented by a homogeneous vector M tilde, ABCD, where we have this expression AX plus BY plus CC plus D equals 0. That has to be fulfilled for all X, Y, C, where these points are on the plane. And we can equivalently write this compactly as this homogeneous constraint. Again, we can normalize M tilde so that M tilde, or so that N, this three-dimensional vector, the Euclidean norm of N is equal to 1. And in this case, again, N is the normal perpendicular to the plane. Now, not the line, but the plane, and D is the distance to the origin. An exception is the plane at infinity, which passes through all ideal points, or points at infinity, for which W tilde is 0. Here's an illustration. I mentioned before that I show an illustration for lines, but I omitted that. I just directly have the illustration here for planes, but it's the same, just one dimension higher. So what we have here is this coordinate system here, and we have this plane here, which is at distance d from the coordinate system if this n vector here is normalized to 1, and then n corresponds to the normal of that plane. Okay. Now 3D lines are a little bit less elegant than either 2D lines or 3D planes to express. One possible representation is to express points on a line as a linear combination of 2 points, P and Q, on that line, as done here. It's this convex combination. However, this representation uses 6 parameters for 4 degrees of freedom. A 3D line has only 4 degrees of freedom, and we're using 6 parameters here, which is not ideal. There's alternative representations. There's multiple alternative representations. One is, and one minimal representation is the 2-plane parameterization, and another one are the Plücker coordinates. And there's more details on this in Zelinsky and Hartley and Zisserman in chapter 2. The 3D analog of 2D conics are quadric surfaces. So here we have a variety of quadric surfaces that can be expressed as these quadratic equations here with homogeneous coordinates in 3-dimensional space. So we have a quadratic expression here, and all the points that lie on the surface of these quadrics, depending on Q, this quadric shape changes, but all the points for a particular Q, all the points, let's say in this case, in this parabola case, all the points that lie on the parabola surface satisfy this expression. Now these quadrics are useful in the study of multi-view geometry again, and they also serve as useful modeling primitives for understanding scenes in terms of compact representations. Here's a simple example from my research group where we have used superquadrics, which are a slight generalization of these quadric surfaces, in order to represent geometric objects in terms of simpler parts. So here you see some meshes, you see representations in terms of simple cuboids, and then in the bottom in terms of superquadrics. And this is very useful for understanding the world in terms of simple primitives, and can be extracted in a pretty unsupervised fashion, and allows for shape abstraction and also compression. We can then compress scenes very compactly and store them very compactly while still preserving the dominant semantic meaning of the scene. Okay, so let's move on to transformations now. In this unit, we're going to discuss the most important 2D and 3D transformations. So we're going to start with 2D transformations, and the simplest 2D transformation is clearly a translation, where if we have a square here, we're simply translating that square to another location in that two-dimensional space. And such a translation is simply given by adding a two-dimensional vector in inhomogeneous coordinates to all the points that we'd like to translate. And we can alternatively write this as this homogeneous expression here, where here on the right we have a 3x3 matrix, and we're converting a homogeneous, in this case an augmented vector, to the new location by multiplying it with the identity matrix and adding the translation. Now see that the translation here is added because the last element of this augmented vector is 1. So we're multiplying 1 with t, and we have the identity here. So we're taking the original point and adding t. So it's a simple 2D translation with 2 degrees of freedom, tx and ty. Now, using such a 3x3 matrix here instead of this allows us to very easily chain or invert transformations. So we can compute the inverse translation by inverting this matrix, and we can chain multiple translations by multiplying multiple of these matrices together into one matrix that then represents the chained overall transformation. And this is not only true for the simple translation example, but for all the other transformations that we are going to see: Euclidean, similarity, affine, and projective. As always, augmented vectors can always be replaced by general homogeneous vectors, x tilde. The next transformation is the so-called Euclidean transformation, which is a translation and a rotation. So it has 3 degrees of freedom in 2D space. And this can be expressed as Rx plus t in homogeneous coordinates, or in homogeneous coordinates by a matrix where in the top left 2x2 submatrix we have the rotation component R, and then in the top right we have the translation vector, the two-dimensional translation vector. And if we multiply this with an augmented vector, we see that we obtain this expression, Rx plus t. R is a rotation matrix from the special orthonormal group SO2 with the properties that R transpose is equal to the identity, so it's orthonormal, and the determinant of R is 1. Euclidean transformations preserve Euclidean distances. So if we look at 2 points that are at a certain distance after the Euclidean transformation, they are also at the same distance. And this of course holds also for the translation, because translation is a special case of the Euclidean transformation, but it doesn't hold, for instance, for the affine transformation. So we see already that this is giving us a hierarchy of transformations that we're looking at here. The next level is the similarity. The next level in this hierarchy is the similarity transformation, which is 2D translation plus scale 2D rotation plus 2D rotation plus scale. So it has 4 degrees of freedom, and it's exactly the same expression as before, except that now we have a scale that's multiplied to the rotation before translating the vector. Again, R is a rotation matrix. Now S is an arbitrary scale factor. It's a scalar. And the similarity transformation preserves not anymore distances, but at least angles between lines. So we have, for instance, an orthogonal relationship between these 2 lines here, which is preserved from the original cube. But the scaling has changed, and the rotation and the translation. Now, going 1 level up the hierarchy, we have affine transformations, which have 6 degrees of freedom, where now the rotation matrix here has been replaced, this 2x2 matrix, with a general arbitrary 2x2 matrix. So we have 4 degrees of freedom here and 2 degrees of freedom here. But here at the bottom we have a 0 vector and a 1. So overall we have 6 degrees of freedom. And we can see an example of an affine transformation or a linear transformation here. which is not preserving angles anymore, as you can see, but which is preserving parallel lines. So if you have two parallel lines, then these remain parallel with respect to each other after the transformation. And then finally, the most general transformation that we can define with such a linear homogeneous equation is the so-called perspective transformation or homography. And an example is given here. Now, every point can transform, every point on this square can transform to a different location. That is why we have 8 degrees of freedom. We can also represent this by the coordinates where every of these 3 corners of the square transforms to. But it's only 8 degrees of freedom. So all the points that are in between or outside would transform similarly to these transformed corners of the square. And so this can be represented by a 3 matrix, which is a homogeneous matrix that is defined only up to scale. That is why this matrix doesn't have 9 degrees of freedom, but only 8 degrees of freedom. It's a homogeneous matrix. So all the matrices that are scaled relative to each other, but are otherwise the same, are in the same equivalence class. So this property, this principle of homogeneity doesn't only apply to vectors, but of course also applies to matrices. Now, this is an equation here that is in terms of a general homogeneous vector. And of course, we can again obtain the augmented vector by dividing by the last element as we've defined in the beginning. Perspective transformations do not maintain parallel lines anymore, as you can see, but they preserve straight lines. So if a line has been straight in the original before the transformation, then after the transformation it's guaranteed to also be straight. It's not bending. It's a linear transformation in homogeneous coordinates. Now, we've seen how points can be converted into new points using such homogeneous transformations. But what happens with covectors? Lines are covectors because they are represented by a vector that is used always in combination with a homogeneous coordinate to define a useful principle such as a line equation. And so what happens with, for instance, lines? How can we transform lines with these homogeneous representations? Well, considering any perspective 2D transformation, what we can do is we can look at the transformed 2D line. And the transformed 2D line equation is simply L tilde prime. This is prime indicates that this is the transformed line, transpose times x tilde prime. Now, we know what x tilde prime is because that's what we have just defined, the perspective transformation. So we can plug that in here. And then we can multiply these two together or factorize them out and obtain H transpose L prime transpose, if we transpose this expression here. And this, as we recognize, is simply the line equation if we set it to 0. This is what we started with. This is our assumption, that this transpose x tilde is equal to 0. So this must be the expression of the line before the transformation in homogeneous coordinates. And now we see that, well, L tilde transpose is this expression transpose, which means that L tilde prime, this is the transformed line, is equal to H tilde transpose to the power of -1 times L tilde. Therefore, we see that the action of a projective transformation on a covector such as a 2D line or 3D normal can be represented by the transposed inverse of the original matrix that is transforming points and can be easily obtained and applied. So here's an overview of 2D transformations. We see the hierarchy, translation, Euclidean transformations, similarity transformation, affine and projective transformation. We see their representation. We see the degrees of freedom. what they preserve, and here an illustration of what they do. So we see that these transformations form a nested set of groups, which is closed under composition and inversion. So these are defining mathematical groups, and they can be interpreted as restricted 3x3 matrices operating on 2D homogeneous coordinates. So this is the least restricted transformation or least restricted group of matrices. And the more we go up in this hierarchy, the more restrictions we have. Here the restriction is that the top left of the matrix is an identity matrix. And while these matrices here are written as 2x3, we can always add a last line 0 and 1 to make this into 3x3 full rank matrices. The transformations preserve the properties below, which means that, for instance, the similarity transformation does not only preserve angles, but also parallelism and straight lines. Right? And the translation operation does not only preserve orientation, but also all of the other nested transformation properties. So the translation preserves almost everything except translation, and the projective transformation only preserves straight lines. And the same holds true for 3D transformations. So here's an overview over the equivalent in 3D space, where the degrees of freedom changes, but otherwise is very similar. Again, these 3x4 matrices that you see here can always be extended with a fourth row to apply them in homogeneous transforms and to change transformations, etc. Now, let's go back to the 2D case. And let's think about how we can actually estimate the parameters of these transformations given some observations. And while this is possible for all the transformations, we are going to look here just at the most general transformation, which is the perspective or the homography transformation. And we already know that this homography has 8 degrees of freedom. So if we want to estimate this transformation from correspondences between a representation before and after the transformation, between two images, let's say, then we know, because each pixel defines two constraints, a constraint for the x and the y coordinate, we need at least 4 of these correspondences in order to properly define and estimate the homography. So let x denote a set of n 2D to 2D correspondences related by this homography equation in homogeneous coordinates, where x tilde is the point, the ith point before the transformation, and xi tilde prime is the point after the transformation. And we need at least n equal 4, but we can have more. We can have an overdetermined system to obtain a better homography. As the correspondence vectors are homogeneous, they have the same direction, but they differ in magnitude. Right? So we have represented this equation here in homogeneous coordinates. So now, in order to solve it, we cannot just set the left side equal to the right side and solve for this, because there is more flexibility in it. We have to account for this flexibility. And the simplest that we can do for this is we can rewrite this expression, we can rewrite this equation as the cross product between the transformed point and the point before the transformation multiplied with the transformation matrix. And that must be equal to 0. And the reason for this is that in the cross product of two vectors is 0 if these two vectors are pointing in the same direction. But it doesn't depend on the length of these two vectors. So this is a more convenient expression for us to work with, because we want to make sure that these two vectors, x tilde and x tilde prime, are homogeneous vectors, so they can scale arbitrarily. So this is the term that we are concerned with. Now, using little h tilde k transposed to denote the kth row of h tilde, this can be rewritten as a linear equation in h tilde. And this is what this equation looks like. This is just rewriting this cross product if you multiply this, you will see very easily that this corresponds. Now, this is nice because now we have a linear system where this H vector is the unknowns that we want to solve for. And here on the left, we have a matrix of, like we have this system that we use for solving for H. So we have, in other words, we have a linear system A, H tilde, that shall be equal to 0. Now the last two rows are linearly dependent up to scale on the first two and can therefore be dropped. The last row is linearly dependent up to the scale on the first two rows and can be dropped. Sorry. And so typically what people do is just consider these first two rows. So we have a 3x1 vector h1 and a 3x1 vector h2 tilde and a 3x1 vector h3 tilde that is multiplied with this row. And this is a 2x9 matrix. So each of these elements here has 3 columns and we have 2 rows. That means, as expected, we obtain 2 constraints per point correspondence, per I, where we can now stack all of these correspondences into a bigger matrix to obtain a determined or overdetermined system that we can use to determine the vector H. And that is that contains the elements of the matrix H. So each point correspondence yields 2 equations, and stacking all these equations into a 2n times 9 matrix, for instance 8 times 9 matrix, A leads to the following constrained least square system, where we have H star, this is the solution to that system, is the minimizer of this expression with respect to H tilde. And this expression simply says, well, because we want this to be 0, we want the squared error of A H tilde to become as small as possible. So this is the L2 norm here. And we want, at the same time, we've introduced a constraint that fixes H tilde, the norm of H tilde, to 1, as the H matrix that we try to determine is inhomogeneous. And this is how we homogeneous. This is how we introduce this constraint and constrain this matrix, because otherwise it would be unconstrained and only defined up to scale. And we have to constrain this matrix to one particular solution out of this equivalence class. And we do this using this Lagrangian formulation, where we have this Lagrange multiplier here. So this is a standard constraint optimization formulation with lambda times h minus or h squared minus 1, where this term here vanishes if the norm of h is exactly equal to 1. And if we take the gradient of this, we arrive at this expression here. No, that's not true. What has happened here is only I've rewritten the expression on the top without the square, right? So this is just rewriting it in terms of standard linear algebra. So we have h squared is simply h transpose h, and ah squared is h transpose at times ah. Okay. Now, the solution to this optimization problem is the singular vector corresponding to the smallest singular value of A. In other words, the last column of V when decomposing the matrix A as a singular vector decomposition U d V transpose. And this is very similar to what we have discussed in the deep learning lecture 11.2 in the context of PCA, except that here we're using a singular value decomposition instead of an eigenvalue decomposition, but we could also use an eigenvalue decomposition of the matrix A transpose A, which is equivalent to a singular value decomposition of A. Yeah. And why do we have to use the singular value decomposition here? Well, we see that this is an eigenvalue problem. If we want to minimize this expression and we compute the derivative of this expression with respect to h, we see that we end up with an eigenvalue problem, as in the case of PCA. We have AH equals minus lambda h, and this corresponds to a eigenvalue problem. Good. The resulting algorithm is called a direct linear transformation. So this is a very general algorithm that not only applies to homography estimation, but in general applies to this estimating in closed form solutions to systems expressed in terms of homogeneous coordinates. What can we do with this now? Well, and this is also something you're going to do in the exercise, we can now define correspondences between two images. So we have two images here that are taken from the same viewpoint. That's important. You may not translate, because otherwise the projective geometry doesn't work. They must be taken from the same viewpoint, but they can be taken in different directions. So you can rotate yourself around your own axis. And what we want to do now is we want to stitch them together into a panorama, as your camera stitches images that you take into a panorama. And for that, we can determine correspondences. For instance, we can mark this point on the hill and this point here, and maybe this point here. Well, this is not visible actually. So this point here and this point here. So we can determine 4 such correspondences between these two images. And then using SVD, solve for the matrix A, solve for the vector H, which defines the homography H. And then we can warp one of these images into the other image space and combine these two images into a larger panorama of the scene. And this is very standard today. Almost every smartphone has the possibility to create such panoramas from multiple images.